You're an orthopedic surgeon, one of the lucky ones, with access to a high-end robot for joint replacements. You've templated the case, reviewed the scans, built the plan. Now, the robot is live, synced and ready. You guide the burr. It pushes back if you drift. Every movement has a boundary. Every cut has a confirmation. And when the resections are done, they match the model to within fractions of a millimeter. That's what robotics brings to the OR. Precision, reproducibility, confidence, especially in total joints, where millimeters and fractions of angles matter. And the difference is real. Robots have raised the surgical floor and the ceiling, improved alignment, reduced outliers, and standardized consistency across surgeons, hospitals, and systems. But as robotic surgery becomes the new standard, a deeper question starts to surface. What exactly are we making more precise? Because the robot doesn't choose the implant. It doesn't change the design. It perfects what it's given. So if what we're given is still standardized, if the implant is still built for the average, then what are we actually optimizing? That's the quiet contradiction we're exploring today. This episode isn't a takedown, it's a recentering. To trace how surgical robots became one of the most transformative forces in orthopedics, what they've revolutionized in consistency, control, and confidence, and what they've still left untouched. Because the precision is real. But if the part never quite fit to begin with, then even a perfect placement can fall short. This is Unstandardized, Built for One. Episode 4, Surgical Robotics, Precision Without Personalization. Let's get into it. Surgical robotics didn't start with bone. The earliest systems weren't built for orthopedics. They were built for access, navigating soft tissue where a 2 millimeter slip could mean disaster. In the 1980s, platforms like Puma 560 and Probot were developed for neurosurgery and prostatectomies, procedures where sub-millimeter steadiness made robotic assistance life-saving. But bone is different. It doesn't shift, it doesn't swell, it doesn't pulse, it's rigid, structural, predictable. In many ways, it was always the perfect candidate for precision. That opportunity arrived in the early 90s with Robotic, the first robotic system built for orthopedic surgery. Paired with CT-based planner called Orthodoc, it could autonomously mill the femoral canal for cementless THA. No jigs, no reamers, just a preoperative plan executed by machine. Casper followed in Europe, another CT-based robot promising sub-millimeter accuracy, and they delivered on that, in a vacuum. But they were too rigid for real surgery. The bone was predictable, but the rest of the body wasn't. Soft tissue changed, landmarks shifted, exposure varied. Early users saw alignment improvements, but also longer OR times, higher fracture risk, less control once the incision opened. It was precision without context, so the pendulum swung from full autonomy to semi-active systems, tools that partnered with the surgeon, not replaced them. Enter Mako. Rather than cutting autonomously, Mako introduced haptics, a virtual boundary around the planned resection. The surgeon held the burr, but if they drifted off course, the robot pushed back. It was a breakthrough, a robot that enforced precision without taking over control. Mako was FDA cleared in 2008. Stryker acquired it in 2013 for $1.65 billion. Robotic arthroplasty went from niche experiment to industry platform. Other players followed. Zimmer Biomet launched Rosa. Smith & Nephew created Cori. DePuy Synthes introduced Velis. Think Surgical released the handheld T-Mini. Robotics without the capital barrier. Each system took its own path. CT versus imageless, closed versus open libraries, but the goal was the same. Increased consistency, improve alignment, make outcomes more reproducible. And by those metrics, robotics delivered. Dozens of studies now show mechanical alignment within plus or minus 3 degrees, reduced outliers in femoral and tibial positioning, better joint line restoration, more reliable flexion gap balancing, fewer early complications tied to malalignment. Robotics have shown value, not just in primaries, but in complex and revision cases, where jigs and judgment alone fall short. Today, over 1,000 hospitals use robotic systems for orthopedics, most often in total knees, where precision is paramount and error is expensive. Robots are no longer experimental. They're embedded, validated, scaled. They've raised the bar for surgical precision, But precision isn't the same as personalization because the robot doesn't design the plan, doesn't choose the implant, doesn't adapt real time. It executes what it's given, no more, no less. So let's ask a different question. What exactly is the robot following? Let's pick up from the moment of incision. The robot is calibrated, the plan is loaded. Now it's time to move from simulation to execution. That unfolds in 3 steps: registration, bone prep, placement. Step 1, registration. Registration is how the robot matches the digital plan to the real-world anatomy. Even the most accurate plan possible is useless until the robot knows exactly where the bone is. That process starts with landmark probing. The surgeon uses a stylus to identify known points on the patient's bone. From there, the robot reconstructs a coordinate map of the surgical field and aligns it with the preoperative plan or intraoperative scan. Some systems use CT data, others build the map in real time. But in every case, registration is about syncing the virtual and the physical with millimeter accuracy. Errors here are critical. If registration is off by even a few degrees or millimeters, the cuts will follow, but follow incorrectly. Newer systems are introducing ways to close that loop, including autonomous surface mapping, intraoperative 3D scanning, AI-powered registration correction. Because if you lose accuracy here, you lose it everywhere else. The plan might be perfect, the robot might be perfect, but if they're working on the wrong map, precision becomes misalignment with confidence. Step 2, bone preparation. This is where robotic precision becomes tactile. The surgeon still holds the burr or saw, but a haptic boundary ensures resection stays within the virtual plan. Stay within the boundary, you move freely. Drift past it, the system resists. That's the power of semi-active robotics. Surgeon-led execution with machine-enforced tolerance. And in procedures like total knee, where a millimeter of slope or malrotation can change outcomes, that matters. Step 3, placement and verification. After cuts, the robot assists in trialing and placement. Some platforms offer real-time gap balancing, others allow for intraoperative plan adjustments, but across platforms, the goal remains the same: make the surgery match the plan. The robot doesn't close the wound, doesn't decide what to do. It just ensures that what you mapped gets delivered. That alone makes robotics one of the most important tools in modern orthopedics. But it also reveals the limitation. The robot is only as good as the plan it's given. The robot did its job, held the angles, guided the cuts, placed the implant. Everything looked exact. Everything was exact. But that's still only half the equation, because even perfect cuts can land the wrong part. Even optimal alignment can fail to deliver optimal biomechanics. We're placing standardized implants built around the average with sub-millimeter control. That's optimizing execution, but it's not always optimizing outcomes. Every screw might be perfectly aligned, but if the implant doesn't match the patient's anatomy, the result suffers. And that mismatch often shows up after the surgery in recovery, because most robotic platforms don't account for ligament laxity, joint capsule behavior, and the real-time interactions between soft tissues and implants. They give gap balancing data, but based on passive flexion, not stairs, not squats, not lived movement. So the joints can look balanced in the OR and still feel unstable at home. It's not the robot's fault. It's what we've asked of it. The robot controls precision. It doesn't evaluate intent. It holds the plan, but doesn't question it. And when your plan is built on assumptions, even flawless execution can lead to compromise. The next step isn't cutting better. It's rethinking what we're cutting for. Most robotic workflows today still rely on manual planning. A human adjusts implant sizes, tweaks angles, snaps anatomy to the nearest match from a tray. But smarter tools are coming online. Machine learning platforms are being trained to predict ideal implant geometry from CT, simulate joint mechanics under load, recommend resections based on biomechanics and pathology. At the same time, registration systems are evolving too. Autonomous intraoperative scanning, real-time surface mapping, AI-powered correction of landmarking errors. These aren't just conveniences, they're safeguards, and they're starting to close the gap between plan and reality. But the real shift, it's not in the robot. It's in what we give it to work with. Because for the first time, we're pairing custom implants with robotic execution. Personalized geometry built from scratch for a single patient's anatomy, movement, and goals. Placed with sub-millimeter robotic precision, Suddenly, the equation changes. Now, the implant does fit, and the robot doesn't just execute, it delivers something truly individualized. Which brings us to what might be the most important development yet. While not originally the highlight of this episode, recent news has changed that. Monogram Orthopedics, a company that built both sides of the equation, 3D printed, patient-specific implants, and both a semi and fully autonomous robot that places them. In early July 2025, Zimmer Biomet announced their acquisition of Monogram, integrating this end-to-end personalization system into their global portfolio. For the first time, one of the largest implant manufacturers in the world is betting big on a future where precision and personalization are inseparable. By 2027, Monogram's robot is expected to be fully integrated. Zimmer implants will be available alongside custom designs, and the system itself may become the first fully autonomous robotic platform in orthopedic surgery. A robot that doesn't just cut bone accurately, but cuts it for something worth placing. That's the inflection point, and it's already here. So where does that leave us? With the truth we've been circling for the entire first 4 episodes of this series. Surgical robots have changed how we place implants, but they haven't changed what we're placing. They've improved accuracy, reduced variability, lifted consistency across surgeons, centers, and systems. And that's real. But consistency on its own isn't the goal, because the most precise tool in the world doesn't solve the problem if the part it's placing was never quite right to begin with. That's the contradiction we've been living with. Robots have given us precision, but not personalization. We've upgraded execution, but left the design behind. And as long as we're working with trays, fixed sizes, and library matching software, we're still just refining the average. So yes, robotics are a part of the future, but they are not the answer. They are the amplifier. And what we choose to amplify next, that's the real question. That's what episode 5 is all about. The history of custom implants, why they failed to scale thus far, why it is finally their time to shine, and what happens when we stop adapting the body to the part and start building the part for the body. Because if robotics helped us execute with confidence, custom implants may finally give us something worth executing. This is Unstandardized Built for One, the mission to make personalization the standard. I'll see you in episode 5.